This video deconstructs a challenging fluid mechanics question that tests your ability to see a system not just as a static diagram, but as a dynamic chain of events. The scenario is an S-shaped tube with two pistons. The wider piston, arm B, is spring-supported. We add a mass, M, to the smaller piston, arm A, which pushes arm B downward. We need to find the maximum mass M so that the piston in arm B remains just inside the tube. Let's examine the system's anatomy. The vessel is S-shaped. Arm A has area S sub A, and arm B has area S sub B, which is ETA times S sub A. We'll set the factor ETA to 5. The system is initially in equilibrium, with internal pressure balanced by a pre-compressed spring. The disturbance is adding mass M to piston A. The weight increases pressure, pushing fluid to arm B. Piston B moves down by distance L, and the spring compresses by an extra amount L. We must consider the conservation of volume. Since liquids are incompressible, the volume lost in arm A must equal the volume gained in arm B. The volume change in B is S sub B times L. The volume change in A is S sub A times H drop. Since S sub B equals eta S sub A, the fluid drop in arm A must be eta L. Our strategy is to solve by increments. We only need the change in forces for the new equilibrium. We can ignore atmospheric pressure and initial spring compression. The total increment in downward force on piston B equals the increment in upward spring force. The upward resistance comes from the spring. Piston B moves down an additional distance, L. Hooke's law states the force increment is K times L. This force must be overcome by the fluid pressure. The driving force is the downward pressure on piston B. This pressure change results from three factors: the external mass on piston A, the increased depth of the liquid column in B, and the dropped liquid level in A. The core concept is that the extra downward force equals the extra upward spring force. This results in the final equation for mass M, expressed as mg equals KL over ETA plus S sub A times rho HO GL times ETA minus 1. Here are the parameters and constraints. The area ratio ETA is 5. The maximum displacement L is 0.2 meters. The small area S sub A is 0.01 square meters. The spring constant K is 1,000 newtons per meter. Water density rho is 1,000 kilograms per cubic meter, and gravity G is 10 meters per second squared. Now we calculate the limit. We substitute the values into the equation. The left term yields 40 newtons. The right term yields 80 newtons. The total required weight, mg, is 40 plus 80, which is 120 newtons. To find the maximum mass, we divide the weight by gravity. 120 newtons divided by 10 gives 12 kilograms. The maximum mass that can be added is 12 kilograms. This solution balanced mechanical resistance against a complex fluid pressure change, illustrating the interplay of Hooke's law and Pascal's law.